Okay. The crystal's light sensitive inside there, and it's very carefully engineered. Now, to build this sort of thing requires knowledge of physics, real knowledge of physics, solid state physics, in fact, and knowledge of engineering. This is not a trivial thing to build. These things are very, very slick, and they've been engineered to a point where they're wonderful in your camera. Okay, but I don't know what it means to say it's a signal process. I don't know what that is. Anyhow, but they are amazing devices. It's true. Nobody has to know how it works because that's the way our life is now. Everybody's carrying around all this stuff, no idea how any of it works. All right, so telescopes and astronomical instruments. Here is some famous telescopes. For years, this was the largest telescope in the world. This is the Hale telescope in Southern California, the 200-inch telescope. All of you who live in Southern California, has anybody seen this? No. All right. That's a telescope. It's outside of San Diego, and it's in the mountains. It's no longer a great sight because the growth of the area has given us so much light pollution that it's not as pristine as it was. All right, here's a view of the telescope inside. All right, it's a little hard to see that. Let me show you some others. All right, now, what does the telescope do? And you got to remember, a telescope is not to magnify images. We don't magnify images. Instead, we use the telescope as a giant eye to collect the photons, to gather as much light as possible to allow the study of a faint object. It's like your small eye has been replaced by a giant eye. And to produce the images have to be in really fine detail, but they don't have to be big. They can be small, it doesn't matter. It's just magnification. You can do that on your computer. But don't tell people that they magnified the images. They didn't. All right, now, it's important to put the telescope in the right place. You want it to be in nice weather. You don't want to put it in England the way the British astronomers used to do, because it was too hard for them to travel anywhere, so they just put it in a cloudy, rainy climate. Anybody been to England? You know, it never is sunny. The sky is never blue. It's always cloudy. It always rains. Anyhow, you want to be above most of the atmosphere if you can. You don't want to be absorbed by anything. And you want to have the atmosphere be very stable, very quiet. And it doesn't do any good to have the atmosphere jump around at you. And we'll talk about that a little bit more. That's why the telescopes, all the telescopes are on mountaintops. Because on the top of a mountain, the air passing over can be in what's called a laminar flow. And it is not too turbulent, generally. Okay, so light gathering power. If you look at these three views, this is Orion's belt. You can see him around here. Here's Orion, the big guy. And here he is with a little more light. All right. Now, how much light do you get on a telescope? If you have a telescope that's a small area, like this, and you want to build a bigger one, we'll call this D1, D2. All right? The light gathering power varies. Oh, diameter, this way, diameter. Okay, the light gathering power varies as pi d2 or d1 or 2 squared. That's the area of the circle or something. Is that right? Doesn't matter. Okay, so if you want a big telescope, the diameter is big, but the diameter squared is really big. And so you're not, in other words, you grow as a second power of the diameter. to get a big telescope. This one collects light at a certain rate, much less so than this one collects light. So many times you want light gathering power. The biggest telescope we have right now is the Keck telescope with a diameter of 10 meters. 10-meter telescope is from, who can estimate 10 meters? I think that's about it. That's smaller. This is smaller than 10 meters here. Okay? About 8 meters. All right, so the telescope is giant. It's huge. And not only is the telescope a big collection of glass, the glass has to be held to a small fraction of light. A small fraction of the wavelength of light. It has to be incredibly stable. And when you tilt the glass, you take a glass and turn it turn it around as it's tracking something in the atmosphere. It is very difficult to ensure that the glass hasn't bent. It's very hard to find material that's stiff enough that doesn't deform when it's placed in a different gravity load. So the stiffness, building the stiffness behind the mirror is a very fine art and incredible effort. Engineering effort is intense to make these work. But that's what engineers do, and they're rewarded for it. Okay, so when a telescope has a resolution, we say it has a resolution that you write this way. If you take a big telescope and you ask, how well could you ever see on that telescope? How perfect is it? And the telescope will not image everything to perfection. It is limited by this so-called resolution limit, which is written is proportional to the wavelength of light over the diameter of the telescope. So that means that you want this resolution to be very, very small. You want it to get down to a very small size. And to do that, you want as large a diameter as possible. And you want the wavelength as short as possible. Well, X-rays, you can't use X-rays because they don't make it through the atmosphere. You can't use anything bigger than a 10-meter telescope because it's very hard to build a 10-meter telescope's stiffness behind it. But you take what you can get and you find that your resolution is generally not this good. With a big telescope, we should have a resolution that would enable us to see incredible precision. For example, if 1 arc second, you're familiar now with seconds, arc minutes, and degrees. 1 arc second is equivalent to holding a quarter at a distance of 5 kilometers from you. In other words, you have your friend go down to BART and hold a quarter up, and you look at it from top of campus. Okay, can you resolve that? No. You can't generally see that. But you can see about 60 times larger, and that's an arc minute. You can resolve an arc minute, but you cannot resolve an arc second. All right? With telescopes, we typically want to achieve what we can, and a lot of them do not allow us to see much better than an arc second. All right, so here's where it comes in. If you have two objects next to each other, here's one that has a pattern like this. That's called the diffraction pattern. Everything has an image that looks like this. You don't usually see these rings. They're really small. But if you have two together, they say, well, you can just barely resolve this. All right, so the smaller the resolution, the more precise you can see everything. All right, so here's the Keck telescopes. This is the top of Mauna Kea in Hawaii. Over there, this landmass. What's that landmass? No, 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 no. I'm sorry. What is this landmass back here? Anybody? Anybody know Hawaii?
The Big Island?
Well, you're on the Big Island, and you're looking over the ocean. This is all ocean here, to the next island. The next island is Hana. No.
Maui.
Maui. Yes, right. It's Maui. Okay, that's Maui. And the mountain there is Mount Haleakala. Yeah, that's Mount Haleakala. Okay. All right, errors. You know, when you build imperfect images, you will have it will not give you the perfect diffraction limit because polishing the mirrors to the level required is impossible. You just don't do it very well. And you make errors. You make errors while it's being done, and it's very difficult to do it, and sometimes there are substantial errors. Does anybody remember what happened with the Hubble Space Telescope? I don't think any of you were awake then, or were alive, I mean. The Hubble Space Telescope was launched, and then they realized when it was up there that it had the wrong figure in the primary mirror. It was perfectly ground to the wrong figure. And I said, oh my God, how'd that happen? It was a mistake in manufacturing. A mistake in manufacturing spoils a billion-dollar instrument. And people said, I can't believe it. The trouble was that this didn't have a close enough coupling between the astronomers and the engineers doing the work. NASA really screwed up. They wouldn't let astronomers in there. Anyhow, Hubble got fixed in a year or two when they basically sent up something that gave it spectacles. It needed glasses. So they put glasses into the optical system, and it fortunately works. I mean, it would have been terrible for it not to work. All right, so the atmospheric seeing, which is the motivation for the Hubble Space Telescope, diffraction limits. These are what causes the imperfect images. All right, now writing it in a different way, this is putting it in arc seconds. When we have d is 10 meters, and lambda is in some unit, we see that the seeing is dominated. The seeing, that is the turbulence of the atmosphere from motion, is a lot higher than the resolution limit. For example, the Keck telescope should, according to this equation, the Keck telescope should be capable of producing images of 1/10 arc second right away. And yet it never does. It has seeing is that good. It's never 1/10 arc second. It's more likely 1 arc second. Why? Well, it could be 1 arc second because it's not polished right. Errors in the polishing screwed it up. You know, they might have just made a mistake. But actually, the thing that kills the Keck telescope is known as the atmospheric seeing. That is turbulence in the atmosphere as the light comes through. And that is a killer to telescopes, and it can be beat. There's a way it can beat the seeing, but it's very hard work. It's known as adaptive optics. And let me show you a little bit about that. Okay. Optical window. Here, I'll say that again. Okay. Here's an example. Here's an image taken with a ground-based telescope. All right, it's a pretty good image. And here's blown up. All right, so we see that it's a little bit round. The spot is a little round here. But if you have it with adaptive optics in the system, you can actually see this picture turns to this picture. And obviously the later one is better. But how did you do that? it was a magical trick to actually make the atmosphere. You had to measure at about a hundredth of a second. You had to measure what the atmosphere is doing and have a little rubber mirror that takes out those errors. Incredibly fast sensors and electronic systems to make this whole thing work. And it does work. It's difficult, but it does work, and it's the future of astronomy from the ground. Rather than go to all that trouble, people like to put telescopes in space. Right now, they have the Hubble Space Telescope, but that's past its lifetime, and it's going to be turned off. And the telescope that's replacing it, JWST, is having some political trouble. The Republicans have killed it in the House. I don't know whether it's going to die or not, but if it's killed, that's it. You know, astronomy can't do much about it, but you won't be able to make progress unless, well, you know, it's a big target. Anybody know the SSC target? It was a super collider, particle accelerator in Texas. Anybody from Texas? Have you ever seen the SSC? It's a big system built underground. These tunnels, huge tunnels underground. It was a $10 billion project. They had already spent $5 billion, I think, and Congress killed it right in the middle. After they'd already built a lot of stuff. I don't remember where it is. Somewhere in Texas. But that's it's a big state. So, all right, you don't know what's going to happen. All right, here's the trouble with the atmosphere. The atmosphere will cause the light to move a little bit. A pocket of air comes in, and it's a little warmer than the other air. It acts like a little lens, and it causes it to move or bend the way a lens would cause something to move. So it shifts side to side by this atmosphere. And the trouble is that the wind moves these pockets. They're not stationary above us. They're moving across by the wind. And it produces an image that are fairly crummy, like that one. Okay. Now there's other things that really make a difference. For example, this is an issue of spectral resolution. Spectral resolution means how fine can you see the differences in wavelength. For example, you have a system that can produce light. It's really pretty fine. This is 1.54, 0.5, 1.55, and you can sort of see that. But if you had a system with better optics in it, you could disperse the light with finer precision, finer resolution, and turn this into this one. Same object with better resolution. So in astronomy, the optics is constantly something the astronomers are fighting with to try to improve the resolution wherever possible. Okay, so it's an engineering problem that can be very difficult. Okay, but if you can make adaptive optics work, you can make beautiful pictures. For example, here is a picture of Neptune. Neptune, we'll talk about that more later in next week. Here's Neptune with clouds wisping around. Here's without adaptive optics. Here you turn the adaptive optics on, and wow, it's better. Okay, so adaptive optics magically makes the images better. But even without it, you can take amazing pictures. For example, here is the Crab Nebula. The Crab Nebula is what type of object? Anybody know what the Crab Nebula represents? No, don't say. Anybody know what the Crab Nebula was? It's not a star anymore. Well, it was. This is, yes. Supernova. This star was noted by the Chinese astronomers. For some reason, the Europeans make no note of it. This thing got as bright as the full moon and blew up one day in the year 1054. Bang! It exploded, and this is what's left. All right, we'll talk about this later. This is a very important event. And this object is exploding. All this gas is expanding. This is gas of, I can't remember what's what here. All right. This is gas in oxygen lines. This is gas, the blue is, I can't remember what that is. Anyhow, it's a beautiful object. Unfortunately, it doesn't look like much in a telescope. Anything you can see from here is certainly not up to this quality. The same a telescope in the infrared produces an image like this. Looks kind of unusual, but it doesn't bear much resemblance to the first image. If you take an image in the radio region, it again doesn't it seems strange. We'll talk about how the radio emits. It emits when electrons are moving very fast in the presence of a magnetic field. But and then this is an amazing picture here. We'll see more about this in the course. This is the Crab Nebula. This is only the central region, and this is actually the thing that powers it. In the center of the Crab Nebula is a neutron star, and we'll talk about what these neutron stars do. Okay? How they work. Okay, so with the different wavelengths, you see very different objects, and you learn about the details. Now, if you want to see resolution, you can use the following formula. You can say the resolution is some number times the wavelength of light in nanometers, or a wavelength of light is, say, 500 nanometers, divided by the distance in arc seconds. And the resolution could be arc minutes or whatever. So you want the resolution to be as good as possible. But if it's limited by the atmosphere, well, you have to find something else. Now, the problem is, you say, well, how the hell does a radio telescope work when you compare that to the size of a optical telescope? Optical telescope uses very small wavelengths, very small lambdas. Radio telescope will have wavelengths measured in meters. And how the hell does that ever work? I mean, it's not going to be superb resolution, you'd think. It's going to be lousy. Except there's a trick. All right, there's a trick. And the trick is to imagine that each telescope is a part of a big telescope. That's all. You just imagine it's part of it. And then you can actually use that. This can mathematically be done. The beam comes in here. It's recorded. It goes down here. And there's delay lines and in-phase delay lines. And it enables you to actually do things with it. Let me show you some examples. This is the VLA, Very Large Array, in New Mexico. It's on the plains of Augustine, I think. You see, there's nothing. Boy, what a barren place. It's incredible. Now, what is this telescope doing? It's acting as though the whole telescope is as big as this. In terms of calculating the diffraction, the resolution of the telescope is the big one, big telescope. And so this is a technique that is used by radio astronomers to gather fine images. With better resolution, you can see more detail on the object. And so this is used. And there's a lot of electronics in this as well. Okay, these are not toys. These are each 25 meters across, each of these things. They're big. Okay, here is the VLA from the atmosphere, a very large array from above it. The telescopes can be, they're here in a close packed array. That's what it's called. You can spread them out great distances out here and here and here. These arms can be expanded. And they're expanded once a year or so. And yes?
How come it's in that shape?
It doesn't have to be, but they want if you look at a star and the rotation of the Earth goes a certain time, the rotation of the Earth covers like that, then the star, you've now covered what's called the full UV plane. You've seen a star or whatever it is from all these angles, and you put all that information together. It's nice. If you didn't have that, just had one like this, you'd have good resolution in this direction and lousy resolution in the other direction. So they've got to do something like that. And by having this way, they only need 8 hours to get a good scan. You don't need to scan for 24 hours to complete the scan. Make sense? Okay. All right. Here's VLA again. People are down here somewhere. I don't know if that's a person or whatever. All right. Here again. All right, now here is a snapshot of the sizes of telescopes. The Keck telescopes are shown here. This is the telescope owned by University of California, these two telescopes together. This is owned by, this was polished and owned by University of Arizona. All these over here are in the southern hemisphere. These are all in the northern hemisphere, and these are everything we know. Here's Palomar, 5 meter. It's supplanted by all these new generation telescopes. Okay? So a lot of business in terms of these telescopes. Okay, now here is the Keck telescope again. And this is what it looks like. Here's the control rooms. Here's one telescope, there's the other. They're twin 10-meter telescopes. We have two of them because the donor for this project, Mr. Keck, had extra money, I guess, and he just gave us a second check for it. I mean, he only paid $100 million for the first one. The second one he got for a mere $70 million, a bargain. Okay? So if you're ever in Hawaii, you should go up, because you can, as an adult, you can have a tour of the telescopes. Okay. Here's the largest telescope in the largest refracting telescope. Okay. Here's a lens. Here's another lens for the eyepiece, where your eye, put your eye there, and that's it. And this is Yerkes Observatory. It's in Wisconsin, southern Wisconsin. It's close to University of California, University of Chicago. Okay. All right, here is a very large telescope. This is a big engineering effort. Here's a person. This is in the southern hemisphere. This is one in the northern hemisphere. This is in Texas. All right, the Keck, Hubble. This is the Chandra X-ray Observatory. This is a telescope in space that images X-rays. How do you image X-rays? Now, if you've ever gone to you've all had X-rays taken of you. He holds a piece of film or a detector. Nowadays, they put a detector behind your mouth, or you're getting, suppose, X-rays of your mouth. They used to put film back there until recently. Now he puts an electronic sensor back there. And the X-rays shine at you. All right? And then you take an image. and you don't, there's no optics in there. It's just shining direct light at you, and the shadow is cast on this detector, and that's fine. Now, you think of X-rays as being impossible to bend them, but they can be bent. The X-rays can be bent if they pass through a material that is so closely spaced it looks like it is an optical material. So closely spaced, the only way you can make something closely spaced is take a piece of optical, let's see the X-rays coming like this, take a piece of material and turn it up this way. So it's almost, the X-ray is coming down and it goes through a whole lot of atoms that are real close together in projection. Projection is very close and that bends it. If you turn it like this, it goes right through. But if you turn it to a steep enough angle, it will refract the light. And for that reason, that's how it works. Inside of here is such a, whoops. Inside of here are cones that are built up and they're made of material that is correctly refracting for the X-rays. It's astounding that it works. This thing was really difficult to build, but this is something flown by NASA. Okay, the GRO, this is something, it's gamma rays, Compton Gamma Ray Observatory, several detectors up there. Here is the GRO from above. The shuttle took this picture. These are detectors here along this and this is sites of detectors. This for the gamma rays, they don't try, they cannot image them. They just detect them straight out. All right, that's not an optical system. Here is what the new generation space telescope will look like someday. It is amazing construction. If you ever get a chance to read about this, NGST is now known as JWST, James Webb Space Telescope. James Webb is somebody. Somebody in NASA has NASA history. They gave it the name before astronomers could give it its own name. They beat us to the punch. But anyhow, all right, the telescope. This is a telescope. It's made of several, about 6 segments, not the way it's drawn here. And behind it is a blanket. This telescope is always pointed. The telescope does not fly close to the Earth. The telescope flies beyond the Earth, beyond the Moon, beyond a point. I'll have to show you later what it is. And the sun has to be in the background, and the Earth is in the background. And they shine light from down below, hits the blanket. The blanket is made of 1, 2, 3, 4, 5, 6 layers of material that reflect the material, don't let light through, don't let any energy through. And the idea is that this side, the whole front of the thing has to be very cold. It doesn't see light, it has to be cooled down to a Kelvin temperature of 40 degrees. Just out there in space, and it just cools down. And you've got to cool down at the same time that on the other side of it, back here, it's looking at the sun. And it's hot. So it's got to be cold on one side, hot on the other. This is not a simple job. It's a very complex machine. Incredibly complex. I'll give you something to read about this. All right. All right, here is a telescope that is talked about for the follow-on to the Keck telescope. Believe it or not, this is for real. I can hardly believe this myself. These are people. That's a person. And this is something called the California Extremely Large Telescope, CELT. We'll be the Celtics, I guess. Anyhow, this thing is 3 times as big as the Keck telescope. It's ridiculously big. And this thing has to be held incredibly stiffly. You have to hold a secondary mirror up here very well. And this is an engineering monstrosity. It will be extremely difficult to do this for less than $1 billion. Okay, it's a lot of engineers involved in this. I don't know if it's going to happen or not. All right, and here, what is this owl? Overwhelmingly large telescope. This was a dream. Somebody had a dream. This is on the moon, by the way. Anybody want to go and service it? I don't know. That'll cost just a few dollars. NASA will surely launch that for us. Anyhow, that's an idea. Here is an idea that's really going to happen. This is called the SOFIA Observatory, Stratospheric Observatory for Infrared Astronomy. They've flown this. Here is the device. A 747 has a hole cut out of it right here. And the telescope is put in there. It looks in the infrared region. The telescope is flying at high altitude, like the 747s do, way above the atmosphere. And you look out through the atmosphere and see what you see. So the device is to be flown out of California, somewhere in on the west coast. Was it? There's a. It's. What's the field to the west of us near Stanford? There is a. Anyhow, they're put it there. It was built by people here. Parts of it were built here, etc. This is real, and it's going to happen, I think, if NASA doesn't fall apart. Here is an instrument. That's something that was flown once. Here is something called the Giant Binocular Robert Byrd Green Bank Telescope. This is what Robert Byrd gave us after a big telescope we had there collapsed one day in the wind. It was a nice telescope before and all turned into a heap of metal. Just big crash. And fortunately nobody got hurt, but he gave us his telescope. Unfortunately nobody needed it, but we got it anyhow. And it's in West Virginia, his home state. Here is Arecibo. Arecibo is very unusual. It is in a spot in New Mexico. This is in Puerto Rico. Has anybody seen that? What do you think?
That is really big.
Yeah, it's really, really big. These are hills in the topography. These hills are natural. I don't know whether that's.
Mostly natural formation.
Yeah, it's natural formation. It was a natural bowl that was found is in Puerto Rico in these areas full of hillocks, and they suspended from these sites nearby. They suspend materials. Here is the refracting. This is the secondary mirror, and that's the large telescope. It's 400 meters across. It's huge, just gigantic. A radio telescope. Okay. Here are some more radio telescopes. Now, here's a neat telescope. That's a person. All right? This telescope is filled, as is this one. Here's a person, Sudbury Neutrino Observatory. This thing is underground. The previous one was underground. This is in the bottom of a mine. And this material, here's the astronomer, well, there's a physicist here. This whole tank is filled with carbon tetrachloride. Does anybody know what carbon tetrachloride is? Huh? Cl4, CCl4. Carbon tetrachloride is cleaning fluid. The whole tank is filled with cleaning fluid. That's what it is. Carbon tetrachloride smells a little bit, and if you rub it on your clothes, it'll take out whatever's in them. This used to be used as, I think it's a dangerous chemical, but anyhow. What in the hell is all that cleaning fluid doing underground? I mean, there's nothing that has to be cleaned that much. But it's all down there. What's it doing there? All right, we'll talk a little bit about that. This actually is detecting muons. Particles from space come down and they put it underground to get rid of all the junk that's coming with it, and they're trying to filter out what they're looking for. And they were looking for a muonic signal, or actually, no, I'm sorry. They're looking for a neutrino signal that would come down and cause something to happen. We'll talk about that a little later. Similarly, this telescope, Sudbury Neutrino Detector, is huge. There's one of the workmen right here. This huge, under a ton of overburden of stuff. This is way deep in a mine. And the mine, all the ground above it is used to block out all the stuff they don't want to see. They're trying to filter so that the cosmic rays don't get to them. All right? It's incredible. These are all astronomical facilities. Here is, okay, now this is a neat device. This is called Super Kamiokande. It's in Japan. These are all phototubes. They're big devices that can sense a light flash in there. Now, you know what this is here? This is 3 men in a rowboat, or a small rubber dinghy, going around checking the glass, or this sensors, in one at a time. And then they'll fill up a little more and go up higher, higher, higher. This device is a gigantic water tank with very pure water. This is well underground as well, just like the other things. And it detects cosmic rays coming at a certain position, and they can measure them, and they see incredible events. We'll talk about the sort of events you can see with them. It's sort of amazing device in Japan. Okay, this is pretty neat. 3 guys in a rowboat in the middle of a detector. All right, and we have particles in South Pole. Here's an observatory as well. See? I don't know what they're doing. All right, what are they doing here? Underneath them, there are cores that are dug 3 to 5 kilometers straight down cores, and at the end of each core is a region. This is really incredible. These are drawings. That's the Empire State Building for scale. Goes way down, and it has various detectors in it. This is a device that wants to use the ice in the South Pole as an element in a detector. Ice in the South Pole is purified by the pressure above it. It's just a pure ice cube, solid ice cube, and all the bubbles, the air bubbles in ice cubes are gone. It's packed very tight, and this makes it a perfect detector. So they are using that for their needs, for various detection. They're looking for high energy particles. Now, in fact, the interesting thing is that just think what it uses. It's in the ice, not too far. It's down a few kilometers. And it wants to block out the Earth, the junk coming through the Earth. What does it do? It's not looking for things coming down through the ice like they were, not coming from here, but it's looking on the opposite side of the Earth and uses the entire Earth to block the light and then only leave the particles that are left over for them to study. So their primary signal is something upward going, not downward going. It's kind of strange the way this works. But anyhow, that is real. These are all astronomical observatories that are used. Here is an event. It went up I think it did. And this is, all this is a drawing of the event, and here are lights, the processors that went off at a certain time. They went off, snap went off, and tells them a particle came through. So the thing works. Okay. Wow. I wasn't paying attention to how much time went by. But those are some of the amazing devices used by astronomers. And you can see that astronomy, even though it seems like it's a field of no future, is a field that attracts people, and attracts people with big instruments. We got gigantic instruments to enable us to see something. It's not a simple toy anymore. These things are expensive, obviously, and we'll try to talk about what everything is used for. Following the course, we'll see what it does. All right, so I'll see you on Thursday. I'll also send that article to you about the JWST.